modeling, scripting, and high-performance computing for data-driven materials discovery with a focus on nuclear materials, radiation damage, and catalysts. He has published several articles in these fields. Mosab is currently serving as the R&D Global Development Director at Virtual Lab, and he is also in charge of several workshops, computational competitions, and conferences in the field of computational materials chemistry and green technologies. Dr. Minkyu Park has studied computational physics and is focused on thermal transport of nanomaterials, particularly lattice thermal conductivity calculation via classical MD simulations and Boltzmann transport equation. Uh, He acquired a notable knowledge in platform development while he worked in KIST, where he initiated his interest in the MaterialsSquare platform development. Now he works at Virtual Lab as a vice president and in charge of scientific and strategy officer. Moreover, he recently became interested in the development of simulation platform MaterialsSquare and the business expansion to the US and Europe region. Dr. Banisalman, Dr. Park, thank you very much for coming. And now the virtual screen is yours.
Thank you. Okay, thank you for the nice introduction. Can you see my screen now?
Yep.
Yeah, I'm gonna start. All right, thank you. I'm really glad to be here, and thank you for the organizing ChemU. And first time here, and I'm really glad to introduce CATALITIC for all users. So today I'm here. This is Minkyu Park of Virtual Lab. I charge of vice president, and also I'm very interested in development of the simulation platform, especially materials and chemical fields. So today I'm going to share some of the multi-method energy and catalytic simulation platform, CATALITIC. Actually, this is not so very difficult things because I prefer these materials for the very beginner of the simulation guys or some experimentalists. All right, let's start my presentation. So we could measure easily the news of also is global warming. His first article is warned about the climate change will lead to the instinct of the human unless we change. And second article mentioned the climate change can put more insect. And last article is warned about the melting of ice due to the global warming. So we already well know about the climate change affect ecosystem of human. But I would like to emphasize this is not only an old problem, but survival problem now. So people want to change energy source from the non-renewable energy to the green energy recently. So fossil fuels are non-renewable source of energy that produce a harmful emission when burned and is contributing to air pollution and climate changes. By the way, the green energy sources such as the solar, wind, hydropower, and the geothermal energies are renewable and emit very little to the harmful emissions. Therefore, many people are advocating for this transition from the coal, fossil cell, to the green energy in order to reduce the greenhouse gas emissions and mitigate the effect of climate changes. So we cannot resolve all these problems perfectly right now. However, we are familiar with the materials, physics, and chemistry. So to resolve the global problem, let's take a clue from the material. That is why we are developed the catalytics. So materials is very diverse. So you can find this kind of keyword when you are Googling with the climate emergency. So another this first thing is I did the Googling with the keyword of global warming. So you can see many things like planet, environmental action, extreme weather, something. But you can see the CO2, carbon dioxide, fossil cell, and greenhouse gases. It is directly involved related on the materials and chemistry physics, right? So, and also I did a Googling with the keyword of the catalysis and energies. You can see these diverse, is many of the word. So especially you can see the leader part of here is actually, I'm like a scientist of the theoretical part. So I'm very interested in DFT calculations or something like related on the simulations. So you can find many keywords here. So we are starting from the energy problems like global warming, like energy crisis, and we are the find the clue of the solution from the materials, and finally we are like emphasis the energy materials, especially catalysts, right? So, catalyst, about many people already knew about the catalyst, but I want to emphasize, I want to introduce a brief, concept of the catalyst. A catalyst that is that do not change chemically itself and affect to the rate of other chemical reactions, right? So, you can see that this nice figure, and this red or like platinum is gonna be maybe it's a catalyst. And so we also focused on, there are so many types of catalysis, but like photocatalysis and electrocatalysis and medical catalysis and other catalysis. But we are focused on the eco-friendly and green energy effects. So we focused on the electrocatalysis, especially as H2 evolution reactions and or OER or the CO2 alloy, something like that. So we focus on the this kind of the catalysis for the platform. So I briefly also introduced about why we should adopt the simulation to own your research, because us previous like a very classical approach is we call the Edisonian approach. Maybe next presenter will be Mosab. Dr. Mosab also introduced why we should introduce the simulations on your research, but I briefly introduce here. So 200 years ago, so Thomas Edison, which is a very famous guy, scientist, and he invent the light bulb. So he's starting from the he want to find the at that time like a light bulb materials. So he used the like a colleague's hair or something like that. Everything tried to make a light bulb. So we are called that kind of way we call the Edisonian approaches. It means trial and errors. So we want to find some materials which is the superior properties. We always starting from some idea with the domain knowledge and then do some synthesis and measurements. And some case is failure, cannot find the property properly, but in some cases we find a new materials or some new processes, right? But it takes very long time because even though we got some very nice domain knowledge, but we try and error many times. But it's our recently, for example, it's a semiconductor industry or some chemical other things going to be has been changed to the complex process and expensive materials, and also it's uncountable candidates. So this is gonna be the waste of time or some money. So in industrial part or some research part, it's gonna be very big risk. So people think about what is the best way to rapid to make a new to find a new materials or something like that, like a smart. So people think about the simulations. Actually, computer simulation is not only the concept, but also many people are using previously a few hundred years ago. But very recently, the computational resource is going to be very fast and very cheap. So computer simulation, theory-based, the computer simulation is brightened. So this is a simulation. There are some real-world problem like semiconductors or solar cell or even the batteries. We got this kind of real-world problems. So this is gonna be solved by the virtual solution with a theory-based computer simulation. Like we're gonna be solved the Schrödinger equation, Navier-Stokes equation, or Newtonian equation based. So we find the virtual solution within the in the simulation, and then go back to the real world problem. That's gonna be very helpful for your research, because actually it's in the experimental part we need some many manpowers, but it's in the simulation we only one person, one researchers, and we can use many of high performance computer. So it's very smart and it's efficient. So people knows about the simulation is really good and really helpful for the research, but it's very difficult to introduce to own research, because there are some reasons for the introduce to difficulties. First thing is like expensive, like is resource, and second one is domain knowledge, and third one is Linux environment. And when we are doing the simulation, we need some high performance computer called supercomputer. So we should buy some expensive server. At least it costs up around 100k US dollar at least. So this gonna be a big barriers. And second barriers is gonna be the we know the actually in many people know about the chemistry and physics and material science in here, but we should know a little bit different things like a computational physics, computational chemistry, and computational material science, right? It's a little bit different from the your domain knowledge. So we need some more time, about 1 more years to introduce the computer science. And also last thing is gonna be the Linux environment. So we are very familiar with Windows or some Mac OS operating system, but not many people are familiar with the Linux environment. But the computational, like a computational source is under the working under the Linux environment. So we should know about the Linux environment. It takes more than 6 months, I expected. So these barriers are going to be big problem with to introduce the simulations. So Virtual Lab has developed the CATALITIC, which is the cloud-based simulation platform for the energy materials. And this engine is based on the MaterialsSquare-based simulation platform, which will be introduced by the next speaker is Dr. Mosab Banisalman. So I prepared some video of the catalytic. So when you go to catalytic.io, you can register very easily. And this is separate by the modeling lab and analysis lab. So you can see the catalyst modeling now. So in this case, it's platinum iron cobalt is a ratio of 2:3:1. So you can very easily make a like nanoparticle on the website. So you don't worry about any high performance computer or something like that. You only need your like internet enabled computer and also your eyes and your mouse. And when you finish the structure generation, we call the sample simulation modeling, and you can go to the like stabilize, because this sample is very ideal sample, so it's a little bit different from the real world situation. So we just set up the 300k with a 1000 Monte Carlo step. This structure going to be stabilized under the conditions of the 300 Kelvin, and also automatically is a result are shown in the bottom side, and then you can generate the surface. It's all a catalytic reaction is under the surface. We should make a surface of the catalyst. So this is very hard work. So, but in the catalytic platform, you can very easily make a slab like this. After make the slab, you can also doing the relaxations by using the density functional theory calculations. But you don't worry about time consuming or like something like that, because you don't have any times, or so you don't want to calculate density functional theory directly. You can select the AI based prediction models in here. After the structure model relaxation, you can select the reactions like we provide a OR and OER and ORR and CO2RR. It's three reactions provided in the catalytic platform, and you just select the which reaction you want to use, and also in here is there are so many sites of the absorption site, like on top site, bridge site, and hollow site. So in here we suggested some site based on the artificial intelligence, or you can calculate all site by using high throughput calculation on this platform. And also you can set up the pH or some extra potential. And finally, you can get this nice reaction diagram automatically. So this is the catalytic. So it's very brief demo, and I gonna move to the more details. So catalytic is separated by three parts. First one is catalyst modeling, and second part is stabilizing and calculation or predictions. And last part is property analysis. So first part including the make a modeling of the nanoparticles or slabs and molecules on slab modeling in here. Only you need based on the graphical user interface and on the cloud. And go to the second part is based on the this catalyst modeling. You can doing the stabilizing and calculation based on the DFT calculation, or it's an artificial intelligence based predictions. So basically, is stabilizing is doing the Monte Carlo simulation, but more details. This is the grand canonical Monte Carlo simulation. So you only need a temperature and time. And it's like a structure relaxation. We gonna be use the density functional theory calculation with the high throughput calculations. And you don't want to this kind of some first principle calculation. You only select the data-driven predictions. And also it's a catalytic provide a predefined stung model. So you don't worry about any training or some like AI knowledges. You don't need that. And last part is analysis. So you can calculate all things, and it's automatically its catalytic properties are shown, like structural properties from the Monte Carlo simulation, and also its density functional theory calculation, and electronic properties from the density functional theory calculation, and also its AI prediction from the predefined stone model, and also catalytic properties you can get very easily. So first part is the main part of the catalytic. You can go. You are going to the catalytic.io. You can see this kind of display, and so you can see many part over here is definitely. This is the first part. A is the like your credit, and this is the your jobs are running or waiting, and this is your preference, and this is logout page, and main page is separate by two parts I mentioned previously. So modeling RAM and analysis RAM. So I going to be starting from the modeling part. And it's simulation modeling is always starting from any simulation, so you should doing some modeling in order to calculate some properties. So I'm going to start from the catalyst modeling. So this is also separated by many parts, but basically this is the history of your simulation modeling, and this is the new sample button. When you push this one of them of the histories, you can see the modeling, which is the you previously did or done. Okay, so you can press the new button. You can make a new catalysis model, and then you make like I mentioned in here. I forgot this layer here, and you can select the element by a ratio, and also you can make a slab on the like a slab size or some diameter respectively. So you can generate very easily, and otherwise, and also you can get a structure from this structure generator. When you finish the simulation modeling, I mentioned in the previous video clip, you should stabilize your sample by using the grand canonical Monte Carlo simulation. So you just assign the temperature and Monte Carlo step. So this actually is Monte Carlo step is depending on your system size or some materials. So usually 1,000 to 5,000 is enough for the global like relaxations. So when you're done, This kind of stabilizer shows the running or some done. And then when you finish the calculation, you can see that this kind of things. But this part is a left part of the thermal stabilizer. You can see the evolution of the structure changes, and also its energy and radial distribution function as a function of stabilized step. It's a Monte Carlo step. It's same, right? And when you finish the stabilizer, you can finally generate the surface. Because I mentioned is all catalyst reaction is uh, processed under on the surface. You should modeling surface, right? So in the generalized surface part, you can select a part of the your nanoparticle. For example, here or some here or some here. It doesn't matter. So when you select your part of your nanoparticle, it's automatically analyzes your depth profiles, like which depths and which atoms are including in your slab, and then finally you can get a like a very ideal catalytic surface. And also you can don't want this is not really good for the your research, and you can regenerate button over here, and you can make a random structure in order to the ratios by you mentioned previously. Okay. And next part is the sample loader. And you can, I mentioned here is actually Catalytic is a multi-method simulation platform. So it divided by the AI prediction and DFT, which is the first principle calculation. So if you want to predict here, and you can press just button here, and then you can get electronic structures and reaction diagrams in here. But this is the just prediction, and this is based on our stock model. Our stock model is based on also based on the more than 20K data DFT database. So it's pretty sure that it's very high accuracy we expected. Otherwise, you can doing the relaxation button here. So after the select your method, and you can get a like a density of state data, or also is a dependent center analysis of some of the your structures here, and then you can select the reactions. So, there are many catalytic, electrocatalytic reactions, but we only starting from the ORR is oxygen reduction reactions, and OER is oxygen evolution reactions, and CO2R is CO2 reduction reactions. Only we starting from the three refrigerative reactions of catalysts. And maybe this year we're gonna be expanding more like HL or something other reactions. And also we now we are supported only bare metals or bare uh, uh, that kind of things, but we are going to expand to the oxygen like oxide materials or something like that. And you can select the button, and you can see this kind of displays. And there are many sites, like on top side, bridge side. There are many possible absorption sites existed. So in here, you also check you can select the both button. The subjective is based on the machine learning method, and this is the custom mode. So you can calculate all together, and you just select and the press button is learning simulation. This is fully based on the quantum mechanics DFT method, and high throughput calculation is possible. It means it's all reaction, all calculation are submitted at once. This is really a good thing for the cloud-based systems. So when you done the calculation, you can automatically edit for this kind of reaction diagram. So basically, when we are estimate or compare with catalytic properties, we always use a platinum, right? So platinum is reference materials, and these other things are we designed. So you can compare the reaction diagram by compare with platinum, and also you can get a absorption energy or some which site is stable or not. This is all thing of the catalytic, and I also a few more pages about the strengths of catalyst. Basically, catalytic is the super easy modeling, first of all, and because without domain knowledge, you don't need any domain knowledge of metal alloy, because we print only the combinable elements. So it's not combinable A or B, and you can select B, okay? And only you need a few clicks to generate nanoparticle, and this is quite simple, it's modeling, stabilizing, and done. It's quite easy. And second thing is the automated structural relaxation. And sometimes like a molecular dynamics simulation or some Monte Carlo calculation is quite complex sometimes, even the just relaxation. So you don't worry about this kind of input script. You just put your one temperature and steps. It's gonna be automatically display your result, like energetics or some radial distribution functions. And third one is this is multi-method. It's sort of trend of the simulation. Actually, previously, even the few years ago, people are focused on the first principle calculation, not a AI-based method. But very recently, is many of AI model is developed. So people are combined with the AI and first principle together because of the time consuming problems. So anyone want to just predict the absorption energy or some like a reaction diagram, you can select the AI and then you can check your trend. And most part is of AI will be provided of your like alloy materials. So you don't worry about that kind of things. And also, we already prepare for the more than 20K training set by the DFT calculation. So this is very well trained AI system model we provided. And also, you also don't worry about only AI. You also calculate by using the first principle calculation. So and also AI will be recommend some absorption site in order to the absorption energies. So first part is the fully automated post-processing. You don't worry about any post-processing or like something like that. And also it's very easily calculator by using the high throughput calculation at once. And last thing is gonna be the reasonable price. Actually, you don't worry about any license fee. It's because we are not a software rather than the service. So we set up this kind of platforms as SaaS, SaaS, which is the software as a service. So this is not a software. So you don't worry about any license fee. You only pay for the 100 per month, which is a subscription based. And you want to use more high throughput calculation, you can pay this kind of some metering based pay-per-use policies, but is mostly subscription, including some AI prediction with a very nice trained stock model and 500 CPU hours and 1 TB storages. So we have developed the Catalytic, which is energy and catalytic material simulation platform. And also thank you for the attention today. And I also deeply appreciate for the ChemU peoples. Thank you so much.
Um, Thank you, Minkyu. And now we are going to presentation of Mosab Banisalman. Mosab, you're welcome to present your presentation. Thank you.
Yeah, just thank you, and just give me a minute to share. Just
Um, I'm sorry, currently Mosab experiences some technical issues with his presentation. I hope we will be able to continue in a second.
Yeah, I think now you can see my presentation, isn't it? You must be able to see.
Yes, we are able.
You can you see? Because hello.
Yeah, you can present.
Okay, so I can continue, right?
Yeah.
Yeah. Okay. This is Mosab Banisalman. I'm from Virtual Lab INC, and I would like to continue what Dr. Park has already presented today. He basically presented one of our platform that we have developed recently, which is CATALITIC platform, and it is mainly for OER calculation, ORR, and other kind of catalytic, catalysis related work that many of the researchers in this field would know how it would be important. But today I would like, in this part, I would like to generally go what is virtual lab and which kind of other platforms that would be very important. And I think it would be crucial for many researchers, especially for the people who are just starting their computational work. So Virtual Lab INC, this is, a company that providing 4 different affiliates. One is MaterialsSquare platform. We have another thing, it's called MaterialsSquare Education. We have MaxFlow and MaterialsSquare Consultation. But let's start with MaterialsSquare platform. Maybe some of you would have heard about MaterialsSquare.com, maybe either with some workshop that we have organized several times, or webinars that we are organizing almost every month. But I would like to introduce like what is MaterialsSquare and why we have came into this platform. We know that the current era, we are mainly about advancing the new materials, and these new materials is actually the heart of a lot of industry, either for semiconductor materials, solar cell development, or batteries. So we have always to advance this already developed material to accelerate our products, either like for batteries, for example, to increase the capacity, the charging speed for the solar cell, to decrease the cost and increase the efficiency. Semiconductor, maybe to make it much thinner and enhance its performance for different application. However, we know that there are 2 different approaches, as Dr. Park already mentioned, that Edisonian approach. It's like the bench work, the lab, the actual lab experiment. That if you have, for example, plan to test some experiment, suppose like you have to test what is the best material for water splitting, for example. So you have to get a lot of suggestion based on your study, experience, or knowledge, that maybe materials A, B, C would be one of the potential materials set that we have to test. So you have to go one by one. Okay, so you have to test this material one by one until maybe finally you achieve your potential goal, like the material that shows some promising catalysis for water splitting. But this approach of work is actually known as trial and error until success. It's time consuming, it's heavy, and it would need a huge effort, and of course need time and budget. But it doesn't mean this approach is bad or not, but maybe this kind of approach, maybe partially or even completely, some of this research can be replaced with in silico approach. In silico approach, it's mainly about the computational approach, like where we can employ the high performance computer based simulation, maybe in companion with machine learning package methodology that can try these trial and errors in advance with a computer. Then you can minimize all as much as suggested materials before you go to the actual work. So for example, some of the project, like we have some materials that you want to test if this material is good for next generation memory, or designing next generation memory, like phase change memory. maybe the expected work would be for 6 months for the 29 candidates of these materials. But with using the power of computational techniques and machine learning, we have decreased these materials into only 4 candidates. So we have saving the time from 180 days up to 2 days only, and the manpower from 20 researcher, postdoc, or PhD student into only 1 professional guy who can run this kind of calculation. The space you can work on only on your laptop. The cost would be around $2,000 to $3,000 as compared to the initial cost, which would be more than $100,000. So you can see what is the importance of actually joining this kind of computational work, and how it would be very helpful for your research and also potential project. But if so, like, why we cannot see a lot of people or everyone just easily jump and run their simulation and using the computational tools like density functional theory, molecular dynamics simulation, or other kind of package for their work? We know that every work has its own barriers, and one of the main barriers for every researcher, students or PI, to actually bypassing several well-known barriers for the computational materials or computational chemistry. The first one, which is the equipment, that you have to establish a very expensive facilities like high-performance computers, more than $200K US, plus the maintenance. So you need professional engineers who keep your facilities always in steady mode. The second barrier, also the knowledge. You need someone who actually have grasp some knowledge about computational physics and what is the actual application and how we could apply the computational tools for studying specific physical properties or maybe phenomena. The last one is Linux environment. So you have to deal with the Linux environment. So for anyone who is from maybe Windows environment, like he just knows how to use and control his work using his mouse, of course, this would be a headache for him. So he has to learn first, which could consume some time for him. But MaterialsSquare is actually SaaS, which is simulation as a service. So we provide a unique, and I think it's a novel solution. So these kind of barriers would be waived, actually. So you don't need to worry about how I could design specific catalyst or how I would design this kind of nanoparticle system to the material. It's very easy method or platform. So you can design literally any kind of structure you want by using this platform. And I think in minutes, rather than just you designing your code in the conventional way. So for anyone in the fields of semiconductor metals, polymers in general, he can really benefit a lot from using this platform, either to design his structure and run later on his experiment. There are a lot of papers has been already cited using MaterialsSquare as a platform, either for molecular dynamics simulation, DFT calculation, CalFAD, and other package with like CGCNN, machine learning for materials exploration. There are a lot of universities in the world already using this kind of, MaterialsSquare platform with more than 14,000 researchers who continuously using the platform for their own research. We also, aside from the direct interact with the platform, we have also the team, professional team who can be also guiding your project and experiment for a specific kind of field in materials, chemistry, or physics. So again, this is, the MaterialsSquare is a platform where you can apply any kind of experimental simulation works related to the material exploration, also chemistry application. But it could be, depends on your interest and research interest. Like for my case, I am basically from nuclear engineering background. So I will do a lot of research of like radiation damage and dislocation evolution of the material and strain application for the alloys. And this kind of works I have already published in this works. Also, if you are into the catalysis So you can understand how, for example, water would be interacting with nickel platinum to produce hydrogen peroxide material. This is kind of DFT calculation. Also, you can apply MD reacts calculation. All of these, I'm saying, you can apply easily with Materials Square. Also, DFT pure calculation, you can use to apply the work on Materials Square, like for any other application, even like for 2D materials. I'm just like skimming this one because it could be any work you are interested in. Okay. The second thing, I will show you actually briefly how the platform would be, would look like, the Materials Square, after I finish this presentation. Maybe in 1 or 2 minutes, I will show you. And the good thing on the Materials Square platform, if you are registering from your academic account, like university account or email address, you could get some rewards from the site as credit, and that you can run for specific kind of calculation. We have also Materials Square education. This one, for now, it's for only supported the Korean language courses, but soon it will be available for other language in English and maybe other language as well. But what is the unique on Materials Square education? I think it will be unique of its kind because we are, okay, let me try to share, if I can share. Okay, just to avoid. Okay, I will show this one at the end of the presentation just to avoid any interruption would happen. I will show you what is the Materials Square education and the Materials Square itself. Okay. We have also MaxFlow. MaxFlow is a cloud high-performance computing service. This one is, we are providing unlimited cloud-based high-performance service, MaxFlow. For example, if you are a research center, university, or simply a PI which has a project that he doesn't want to build his own facility, but he has specific licenses for DFT calculation codes package like VASIP or something else, or Monte Carlo, we can compile these codes for you, and you will have simply a very easy access for the high-performance computing nodes, and you can run as you want, freely and anytime, without any worrying about the maybe queues or the speed, etc. So what is the difference between the server availability on premise, like the something which you built by your own cost, or the MaxFlow cloud base? So if, for example, you are building your server, you have some capacity for your server, okay? But this server always on. So it's not always you need this server, which means the availability of this server based on the request of the task that you are running on this server. And sometimes, even if you need to do some calculation, maybe other people, they are doing their job. So you have to wait. And in this case, the availability is very low. And the majority of other CPUs, maybe during several months, no one is actually using. So this is kind of wasting for your facilities. But for MaxFlow, you will use what you want. So if I need maybe 100 cores or maybe 4 nodes for specific calculation, I will use only these 4 nodes. To speed my calculation more, I will increase my nodes, etc. So only you need to use what you want. The difference between on-premise calculation and MaxFlow, so you don't need a space. You don't need initial cost, like you need at least 10,000, maybe from 200 to 10 million US dollar to establish your very strong high-performance computer. But with MaxFlow, you don't need this initial cost. You need just 10 minutes to establish your account, and our engineers would help you to compile your package and maybe other license if you have. And I think this is very successful for research centers who need really external CPUs. As a virtual lab and Materials Square platform, we are regularly organizing workshops. I think this workshop in general, in the core of computational materials, computational chemistry, machine learnings, and all of these trend developed topics by notch speakers. So I think if you are new or already also professional in this field, you would be benefited a lot from joining this workshop. You can register and watch these videos and learn more about what's going on in this field, because this is just recent topics. We're also organizing a monthly webinars for also the hot topic. This webinar is the next webinar would be this month on 28th of March. Would be presented by Professor Adri Van Duyn. I think many of you in the reacts calculation and reacts potential model developments knows who is he. Actually, he's very well known in this field. We also making our regular blogs about the top articles that recently developed and how maybe computational tools are advancing specific field of science, like developing new batteries, developing a new catalyst method, and etc., etc. We also organizing several of activities. Actually, the last one was the MaterialsSquare International Computational Competition about the green hydrogen. So we have asked the researcher to apply their idea in the field of maybe green hydrogen. It could be any of the related, like nuclear or 2D materials, also like the catalyst, any of these topics. So we have selected 10 teams, and every team has awarded 5,000 CPU hour credits on the MaterialsSquare. So now we have those 10 teams. They are actually running their experiment on MaterialsSquare, and for the next round also will be 3 teams selected from them for like further support. This is my presentation for like MaterialsSquare, but I would like to show you exactly how it looks like to use the MaterialsSquare platform. Okay, so let me try to share a window. Okay. Mm-hmm. Mm-hmm. Okay, so I think you can see the screen now. Okay, so the first one is the MaterialsSquare education. Actually, I hope it will be soon available in other language. So in this one, maybe this one course, it's how you can actually, what is the DFT calculation and what is the MD calculation in general. It's talking about like the simulation methodology. It has a lot of topics, and we have very top speakers from Korean universities and institutes. And I would like to show you, maybe you are aware of, okay, just like it looks like this way. Okay, this is maybe you are already familiar with several classes, like how you can understand maybe DFT calculation and maybe other topics. But the good thing in this one, because this is interactive actually course, you can see actually application, direct application, how you can use the platform. And the platform is directly connected to your screen. So you don't need to go for other page to perform your experiment. So now in this class, inside this class, you will see how you can perform maybe titanium oxide, and you can design it, run your DFT calculation, etc. Because I'm using the Wi-Fi. Okay, so you can, maybe I will check this one. So this is my unit cell. Okay, and later on, so this is inside the class now. I'm not talking about the material square itself. I'm talking the class itself, how it would be. So it's very, I think, different than the maybe the known courses here and there. Just you need to maybe enlarge your unit cell. I will make 3 by 3, maybe by 3. Okay, so I have 3 by 3 by 3 unit cell of this material, and then you just go directly go for simulation. And we have a lot of available choices for simulation, either like MD simulation, DFT simulation, or maybe CalFAT calculation, machine learning, and other kind of EMA calculation. In general, if I would like to perform a DFT calculation for the structure, I will go for general. And you have to connect your structure in here. Now your structure is connected, and you will see this kind of form. This is default form, and depends on your calculation request. Maybe I need high accuracy. Okay, high accuracy calculation. You can apply maybe spin polarization, applied van der Waals application. You need ionic and cell optimization, and you have, but in here maybe the screen, because it's small, this is why you cannot see, but here is better. Maybe you have to apply 260 and maybe 100 for these values. And after this, you just tried your experiment, maybe titanium oxide to energy optimization, maybe test. And then you will, and you can select like number of nodes and start. But this is the education version, okay? This is only for Koreans. Again, if I need to go to the actual work application away from the education version, you can go to the MaterialsSquare. So MaterialsSquare, this one is MaterialsSquare platform. This is how it looks like. I think if you register, okay. There's credential. Oh, sorry. This is okay. This one. Okay. Now, this how it looks like to the MaterialsSquare. And when you go to the work in here, you can establish your own work. Like I need new work. Okay. Now, then you can go to the database, or you can decide which kind of structure. Maybe just say I need an NaCl maybe structure. Okay, there would be a lot of available units. So it depends on your experiment and choices and space group that you want and formula. Maybe I just use this one simply, and this is my unit cell. Okay, and then I would like to maybe enlarge. This is just for the purpose of showing. It's not mean that we have to follow these steps for the actual experiment. Okay, now I have this kind of NaCl unit cell 2 by 2 by 2. If you need to do optimization with DFT, you can go this way. There are a lot of possible calculation. You can do NEB calculation, phonon calculation, Raman calculation, high throw throughput for machine learning calculation, or general. This is the general one. You connect your structure. Again, you will have maybe this kind of form, and it depends on your choices and accuracy you are looking for. It's similar to what we have discussed before. This is like the K point, and after this you do paste maybe here and just start job. After you're submitting your job, these kind of calculation would be running on the cloud, and you will see your running job in here. When it's finished, will be finished, and after that you will see there are a lot of analyzer. If you are doing DFT calculation with quantum espresso, you will have many of post-processing codes. And this is how it looks like. After your calculation is done, you will see some result and graphs in here. You can extract, manipulate, and work as per your request. The good thing also, you can, for example, if I need, if I need to add, for example, a vacuum, okay, I will make it just maybe 5 by 5 by 5, and it will be in the center. Okay, so it will be surrounded by this box. If I need to fill, for example, a molecule in here, you just say I need to draw it. There are a lot of methods to draw it. So this is what I mean. It's very easy way to create your structure. Maybe draw a molecule. I would add maybe just say water. Okay, I mean this is hydrogen. Okay, just delete it. I will ask for water, H2O. Okay. You can select, it's either based on density or based on count. So based on density would be like the natural water, 1 gram per centimeter cube, or a number of molecules. I need to add 100 molecules. Okay. So this one, you have the structure of your NaCl in the center and water surrounded by this one. So if, for example, you have to study the interaction between this NaCl and water, which is, of course, not a big I mean, hot topic. This is just for example. It can be any material. For example, if I need to go for lamps, I don't know if there would be any kind of reacts available for this kind of material. Yes, there are a lot of reacts. So you just select, and now you have your reacts, and again, you can do tests. Like this is, I will do NVT calculation or NPT or NVE. It depends on which kind of calculation you need, temperature, time step, also the simulation time expected, and just run. This is how it looks like, okay? Simply and efficiently, you can run your calculation with MaterialsSquare. The platform also has all other kind of option, either the blogs. So if you need any hint, you can see the simulation tips. So we have also module step, like how you can do like the polymer calculation solubility, how to perform the polymer simulation, polymer MD modeling, how, for example, you can do NEB calculation, phonon calculation, optical calculation or optical analysis, density of state, P density of state. I mean, the all kind of well-known DFT or MD calculation, you can have hint and support with this channel. We have also YouTube channel, MaterialsSquare. You can see all of these supports, documents. We have also the workshop, previous workshop, and the webinar. And in here you can see the next webinar and the previous webinars. There are many really notch speakers have been already presented their talks and experience on our platform. I think it's already 5. So this is what I wanted to share with you today. Okay. And I hope maybe these materials and presentation could be of benefits for a few, or maybe for either like early stage learners in this field or like professional. Thank you again. I think I just finished my talk for my part.
Thank you, Mosab. Thank you, Minkyu Park. Actually, you have already answered all the questions in the chat, so I guess everybody can go to the chat and look for them. That's why if nobody has any more answers, let's wait probably 1 more minute until people write their questions into the chat. If they have some, I can highlight them during our stream. If not, then in any case, thank you, Mosab. Thank you, Minkyu, for your nice presentations. I guess I have one more question. I have seen that both, especially MaterialsSquare, it has some interfaces with lamps, with gammas, and so on. do you support all the functionality present in these software packages, or you support only limited number of widely used functions which are possible to use in these packages?
Okay, so I think the general calculation, it's of course it's available either by LAMPS or DFT calculation. So if you have ability to develop or modify your own input, of course you always are able to do any calculation. But for example, for quantum espresso, there are some package which is already developed, like Polstrap, I think lobster calculation. These we are developing and will be integrated soon to our platform. There are already several of package has been developed and integrated in our platform in very efficient and developed way. So I think there are the common calculation, everyone can do it. There are a lot of calculation, maybe not everyone wants, but I think the platform already ready to do several calculation, which is included in several package here and there, and maybe MaterialsSquare make it in easy and efficient way, so you can find it more professional to do it, I think. So maybe if there would be some package that is not yet integrated, it's either no many user using it, or it will be implanted soon if it's really very important for a large scale of research.
Okay, thank you, Mosab. Everything is clear. Thank you, Minkyu Park, once again for coming. I guess this is the end of our ChemTalk 3. I invite you to the next ChemTalk. It will be held on 15th of March. And see you soon.
Okay, thank you. Yep.
Thank you so much.